Hi, welcome to this presentation titled Energy Release Patterns and Shaking Effects of Earthquakes in the Japan Trench, a Hilbert-Huang transform approach. I am Swapnil Mache, a master's student at the Indian Institute of Science, and my co-author is Professor Kusala Rajendran, also at the same institute. Through this study, we propose a Hilbert-Huang transform-based algorithm to obtain the energy release at the earthquake source and represent it using a function we call the energy rate function. This energy rate function matches well with the moment rate function we obtained from teleseismic waveform modeling in terms of its shape and duration. We demonstrate our approach through the analysis of 5 earthquakes from the Japan Trench. This is an outline of our presentation. First, we look at some critical points behind the motivation for this study. Then we discuss the key contributions of our work. Next, we briefly discuss the two distinct data sets used in this study along with their corresponding methodologies. Finally, we present and summarize the results of our analysis. Previous studies have observed that earthquakes occurring in subduction zone environments showcase heterogeneity in their energy release patterns and frequency content depending on the tectonic setting and depth of origin. We consider earthquakes from 3 tectonic settings: interplate, intraplate, and intraslab. Interplate earthquakes originate on the interface between the two interacting plates of the subduction zone. Lay et al., in their study of interplate earthquakes in different megathests across the world, defined 3 principal domains based on the hypocentral depth. They observed that the high frequency energy and energy to moment ratios increased with depth. Ye et al., in another study, analyzed outer rise intraplate earthquakes, which are sourced away from the trench towards the sea. They reported enhanced high frequency energy and ground shaking from such events despite their high epicentral distances. Finally, we consider intraslab events, those that occur within the subducting slab and usually beneath population centers. Intraslab earthquakes are much more damaging than similar magnitude interplate events and pose a higher seismic risk owing to their higher frequency of occurrence. They also release enhanced high frequency energy in a short duration with high stress drops observed to increase with depth. The different characteristics of events originating in different tectonic settings and at varying depths are usually studied using conventional methods like the Fourier transform, short-time Fourier transform, and the wavelet transform. These methods are not completely suitable for nonlinear and non-stationary earthquake signals. They have limited resolution and a priori defined bases. In this study, we leverage the advantages that the Hilbert-Huang transform, or HHT, offers over the conventional approaches. HHT is a combination of empirical mode decomposition, or EMD, and Hilbert spectral analysis. EMD has an adaptive basis, and the Hilbert spectrum provides improved resolution in the form of the instantaneous frequency and energy. Moreover, we use strong motion data to represent the earthquake source, where usually teleseismic waveform modeling is used. These are the key contributions of our study. Using the Hilbert-Huang transform, we generate the energy rate function, which we consider to be representative of the energy release at the earthquake source. We validate this by comparing energy rate functions generated from 5 earthquakes with their corresponding moment rate functions. To generate the energy rate function, we rely on decomposing the earthquake signal into multiple frequency components or intrinsic mode functions using empirical mode decomposition. We find that specific intrinsic mode functions, or IMFs, capture the energy release well. Moreover, we find that the match between the two is also controlled by the selection of stations. We introduce criteria for the selection of stations for strong motion analysis and the selection of IMFs. Here, we analyze 5 earthquakes from the Japan Trench, 2 intraslab, 2 interplate, and 1 intraplate event. The figures on the right show the event locations in plan and cross-sectional views. Our analysis is based on 2 datasets: teleseismic data from IRIS, that is the International Research Institutions for Seismology, and strong motion data from the KiK-net seismograph network of NIED Japan, that is the National Research Institute for Earth Science and Disaster Resilience. KiK-net has borehole sensors at depths of more than 100 meters, and we use the vertical component waveforms from these borehole sensors. This table shows the details of the 5 events that we consider. The details are taken from the Global Centroid Moment Tensor project. Coming to the methodology, for waveform inversion, we use the Kikuchi-Kanamori body wave inversion program. Through this analysis, we obtain the fault and slip models and the moment rate function. In the figure on the left, we can see a standard result from waveform inversion for the event marked by a red rectangle in the map on the right. This event is the 2011 Miyagi intraslab earthquake, and we demonstrate further steps involved in our analysis using this event as an example. The dominant strike of the Japan Trench provides a crucial starting point in the selection of stations for strong motion analysis. Stations approximately orthogonal to the strike give optimal results. We utilize the slip distribution generated from waveform inversion, shown in the figure on the left, to obtain the station's desirable azimuth. In addition to this, we also employ seismic intensity distribution maps from the Japan Meteorological Agency, or JMA, to select station locations that observe high seismic intensity. The figure on the right shows the event and the corresponding station plotted over the shake map, a shaking intensity map from the United States Geological Survey, or USGS. For the selected station, we use the acceleration waveform from the vertical component of the borehole sensor for further analysis. The first step in this analysis is the decomposition of the signal into its multiple constituent frequency components called Intrinsic Mode Functions, or IMFs. For every event station pair, we validate the decomposition algorithm by comparing the sum of all the IMFs with the original signal before proceeding. The figure shows the decomposition and validation steps for the 2011 Miyagi intraslab earthquake. Next, we introduce a criterion for the selection of IMFs that could possibly represent the source. We select IMFs in the frequency range of 0.1 to 3 Hz, which corresponds to the bandpass filtering in waveform inversion. The figure shows the time series, Fourier spectrum, and Hilbert spectrum for each of the 3 selected IMFs. To generate the Hilbert spectrum, we plot the amplitude squared values on the time frequency plane. These amplitude squared values are obtained from the analytic signal for each IMF, which in turn is obtained from the Hilbert transform of the IMF. In the next step, we obtain the new time series and Fourier spectrum from the linear combination of the selected IMFs. The Hilbert spectrum of each IMF is plotted individually, and the Hilbert spectra of all the selected IMFs form a matrix, and the maximum amplitude squared values along the time axis of this matrix are used to generate the energy rate function. So the question here is, can this ERF be equated with the MRF, which is the traditional representation of the source? Finally, we compare the results from the strong motion analysis with those from waveform modeling. We observe that the ERF matches the shape and duration of energy pulses observed in the MRF. Now we present results from an analysis of 5 earthquakes. For each event, the results are summarized in 3 figures. In the figure on the left, we show the shaking intensity map for the event, marked along with the corresponding station used in the analysis. The figure in the center shows the results from the strong motion analysis, with the energy rate function shown at the bottom. Similarly, the figure on the right shows the results from waveform modeling, with the moment rate function at the bottom. For the 2003 Miyagi intraslab earthquake, both the ERF and MRF show a single dominant energy pulse, released over a little more than 10 seconds. The MRF also shows a second, weaker pulse. The ERF captures this weaker pulse, although with lower amplitude, along with a sustained weaker tail. We have already discussed the 2011 Miyagi intraslab event in the methodology section. The ERF and MRF for this event also show a single dominant pulse peaking at the 20-second mark and decaying gradually up to 40 seconds. But the majority of the energy release for this event is observed within 10 seconds. The 2005 Miyagi-Yoki interplate earthquake shows a complex rupture, with a rough MRF also observed by Lei et al. 2012 and Yaginuma et al. 2006. The ERF and MRF from our study match well with those from these 2 studies. We also observe an enrichment in the frequency range of 0.4 to 5 Hz, shown in the Fourier and Hilbert spectra in the figure in the center, which is characteristic of such deep interplate events. We include the 2008 Fukushima Keinoki interplate earthquake as a shallow interplate event, and as is characteristic of such events, we obtain the source energy release with low frequency IMF, which can be seen in the Fourier and Hilbert spectra in the central figure. Comparing the 2 interplate events in this study showcases the depth-dependent frequency variation also observed by Lei et al. 2012 and Ye et al. 2013. Further, we obtain a good match between the ERF and MRF, even with a station located in a region of observed seismic intensity 3. The final event is the 2012 Kamaishi intraplate earthquake, modeled as two independent events in multiple studies. Harada et al. 2013 and Lei et al. 2013 modeled the event as a deep thrust and shallow normal faulting doublet, separated by around 20 seconds. Craig et al. 2014 considered additional cases for sensitivity tests and obtained two dominant pulses of energy release lasting for around 25 seconds in all the cases. The pulses were of approximately 10 seconds each, and the separation between the two varied from 15 to 20 seconds depending on the scenario chosen. Our ERF and MRF show two dominant pulses of around 10 seconds each and a total duration of 30 seconds. This result showcases the ability of our technique to resolve complex ruptures, including those with sub-events. To summarize, the proposed energy rate function captures the source energy release. The HHT-based technique offers higher resolution than conventional spectral analysis techniques. Further, the ERF has several advantages over the moment rate function. The ERF retains the frequency information, is computationally faster than waveform inversion, and does not entail assumptions of the fault geometry and velocity structure. It is to be noted here that our technique is not a substitute to waveform inversion. We obtain the energy release using our proposed algorithm, but we still employ waveform inversion to obtain the fault and slip models. Nevertheless, the ERF can represent complex ruptures like the 2005 Miyagi-Oki interplate event, and sub-events or multiple events, as in the case of the 2012 Kamaishi intraplate earthquake. We also make two improvements in the implementation of the proposed algorithm, to the selection of stations for strong motion analysis and the selection of IMFs. Stations within the azimuth inferred from the slip models, in addition to the orientation of the Japan trench, give optimal results for seismic intensity higher than 3. IMFs selected based on the frequency and energy criterion are used to generate an ERF that matches with the MRF. These are some of the key references used in our work. With that, I conclude my presentation. Thank you.